With the power entrusted by law to the doctorate board, I hereby confer upon you, Aristomenis Ilias Yfantis, born in Athens, the title of doctor from Radboud University Nijmegen, to which are attached all the associated legal and customary rights and duties with respect to academia and society.
In accordance with the customs of this university, I open the ceremony with the following words: Spiritus Sancti Gratia illuminet sensus et corda nostra. Please take your seat. Welcome, everybody. Thank you for joining us either in person or online. Before I give the word to the candidate, I would like to welcome a few visitors we have here in the committee from outside our university. Professor Van Doren from Utrecht University, Dr. Atri from Astron, although we consider her partly us, of course, and Dr. From the Julius Maximilians Universiteit Würzburg. And, not to forget, the co-promoter, Dr. Wilgus from the Instituto de Astrofísica de Andalucía from Spain. Thank you all, and I now give the floor to the candidate for the degree of doctor.
With the permission of the doctorate board, and in order to obtain the degree of doctor from Radboud University Nijmegen, I would like to defend in public my dissertation entitled Dynamical Flows Around Massive Black Holes, Modeling and Inference. So thank you very much all for being here, also for all of you online, and many greetings. A big thanks to my supervisor, my co-supervisor, also to Dutch Black Hole Consortium for funding this PhD, and to the EHT for the collaboration. So let's talk about black holes and accretion. Now, supermassive black holes were discovered in the 1940s, and 20 years after that, it was proposed that the emission we receive here on Earth is due to an accretion disk that you can see on the schematic that emits the light that we receive. Now, from that time till today, many accretion models were proposed that you can see a few examples here. And they all reside in this plot that you can see with energy output on the y-axis and opacity on the x-axis, where in this thesis we focus on the bottom left part with the most see-through disks that we can see all the way down to the horizon. Now, there are three main avenues to do the current modeling nowadays, but we focus mostly on the semi-analytic models that you just provide a simple structure for the plasma, and any dynamical component needs to be added by hand, as I'll show later, and we briefly touch on GRMHD simulations. Now, we explained briefly about the disk structure, but of course there is the emission part too, and in the disk we study, this is mainly synchrotron radiation, where it happens when charged particles, such as protons and electrons, are being accelerated near magnetic field lines. This produces an emission that is linearly polarized. And when I talk about linear polarization, I refer to the electric vector position angle, here shown in red, or EVPA, that we commonly analyze in the two components, Stokes Q and U. That will become quite useful later in the presentation. Now, in the first chapters, we will be focusing on Sagittarius A star that you can see in this beautiful picture from EHT with linear polarization ticks with this brush stroke. That is the supermassive black hole at the center of our own galaxy. Now, in the chapters to follow, or in this thesis, we use data from 3 different arrays in chapter 1, 2, and 3. The ALMA telescope in radio, the VLTI, or gravity instrument in near infrared, the Event Horizon telescope, and we also made a bonus track, let's say, where we analyzed an observation that hasn't even happened yet, but we hope it will. So I explained a bit about the disks and the emission and the data, but we also need a method to compare, and for that we use Bayesian statistics throughout this thesis. So in short, in the following, I present novel methods and algorithms for data comparison using various models of accretion. And let's jump straight to the results. The first chapter, fitting the ALMA data with a hotspot model. You can see here in this publication from my co-supervisor in 2022. After an X-ray flare, the 2 components of the linear polarization, Stokes Q and U, show this nice sort of coherent behavior, this somewhat sinusoidal character. And if we plot them together in the Stokes Q and U in the y-axis plot, they make this famous QU loop. I will also call them pretzels due to the small bump there. So there was a concept model to explain this emission, a hotspot at some point being a rise in the flow near the event horizon, or the main flow, a hot blob of plasma moving for roughly an orbital period, recreating this type of observation. In our work, we simulated this with a bit more detail. We added, of course, a lot of parameters for the plasma physics and some dynamical parameters, such as the inclination of the system, the orbital velocity, the distance of the hotspot from the black hole, cooling, and so on. So we want to cover a big range of parameters to see what fits best of values. And so in order to do that, we created an algorithm called BIPOL for Bayesian IPOL, where IPOL is the general relativistic radiative transfer code written from my supervisor back in 2018, combined with Dynasty for the Bayesian estimations. And you can see a simple schematic of how, using the real data and our model, the sampler chooses different values and slowly converges to the best parameters. Now let me jump to the best fit model that I show here in this slide. You can see on the simulation domain the hotspot moving around the black hole, and on the right, using the best parameters for this type of model, how well we can recreate the observational data. Here they are, all of them together. And so from this first part, we made some estimations, such as the inclination at 160 degrees, corroborating with previous studies. We found the distance from the hotspot from the black hole. And importantly, we identified that it's really strongly favored for the hotspot to move in a sub-Keplerian velocities that really points towards a certain type of accretion disks with very dominant magnetic fields that we call magnetically arrested disks, or MAD models. And we even found the best orientation for this magnetic field. Now, a year after the initial publication from ALMA, the gravity collaboration also published some similar results that you can see here in the top right plot, the polarimetry again, the QU loop. And they also added astrometry following the brightest image, the brightest spot in the image throughout the observation. And using a fairly simple model, they made this sort of fitting themselves. So then Maciek came to me and said, hey, we can model this. I said, okay, let's do it. This is how our second project started. So I'll skip again to the main results that we obtained from this fitting. And you can see we made 3 models with different velocities, really trying to pinpoint which one is favored. You can see in the best model, they're all kind of match the observations. They also have much larger error bars than the previous one. But notably, for us, the QU loop is rotated for roughly 100 degrees. So the position angle of the system is different, and we have a more wobbly situation going in the astrometry plot. So from our analysis, we're able to say that in the gravity fitting, we believe that super-Keplerian motion for the hotspot is favored. And you can see that our ALMA fitting matches pretty well with the gravity fitting, but when we do the gravity fitting, we end up in somewhat different parameter space. This could be explained from different effects on the accretion disks, which I don't have time now to dive into, but perhaps in the future, with common observations, simultaneous observations of ALMA and the gravity instrument, we would be able to decipher this issue. Okay, briefly, I'm going to mention in the third chapter where we tested the Bayesian algorithm for GRMHD models. And you can see here a tiny fraction on the top of the EHT library created of GRMHD models to fit to the Sagittarius A star image. And so we wanted something faster, a Bayesian automated algorithm. But of course, this is very expensive to happen because these models are much more complex and computationally expensive. So we only managed to do that in synthetic tests where we know the truth and we try to make our simulations fit to this truth without them knowing it. And we identified that to move towards real data inference, we need a better error understanding and manipulation in the data side. So with that, allow me to jump to the final chapter of my thesis, where we propose a spin estimation from a hotspot observation using an empirical relationship. So if we're lucky at some point and we have an imaging campaign at the same time where a flaring event is happening in Sagittarius A star, we would see, hopefully, of course, the hotspot on one side of the disk. But perhaps if the hotspot is bright enough, we would even be able to see the secondary image of the hotspot, seen here with the left arrow, where from the photons that travel half a circle behind the black hole and then reach the observer. Here you can see this also in the simulation domain. And so we thought that if we measure the difference in position angle between the first and the secondary image, we would be able to tell something about the space-time. So once again, using IPOL, as many times in this thesis, we create a library of roughly 1,000 models, varying these 4 key parameters for the hotspot. And you can see again in one simulation with high inclination how the hotspot is moving and the secondary image in response. And we're tracking the delta PA in every time step. Jump forward, we took all the results from that. We tried to look for trends on all the parameters, how the delta PA varies when they vary. And we ended up with this fairly simple equation for a delta PA with respect to spin, sort of like a linear relationship, in contrast to the many pages of papers usually try to analyze this problem. But we also need to know how well this does. So here you can see the simulations in color for different spins and different radii fixing an orbital velocity. And with X, our empirical fit usually matches the observed delta PA in less than 4% errors or less than 4 degrees deviation. So in the future, with the EHT, now also plus Namibia, a telescope also being developed here partially in Radboud, or with another project like the Black Hole Explorer, if we have a delta PA measurement of roughly, let's say 100 degrees as an example, and normal errors of 5% for the delta PA and the rest of the parameters we need, we theorize that we will be able to contain spin with 2 sigma confidence roughly plus or minus 0.3, which is quite better than what we are able to do right now. So just to recap, this thesis used the hotspot model to do trivial data fitting from the ALMA and gravity, obtaining realistic parameters. It proposed a spin estimation method using a semi-analytic relationship, and it made the first step towards Bayesian inference in GRMHD models. So thank you very much for your attention. And having presented this summary of my dissertation, I return the floor to the rector.
Thank you very much. The opposition will be started by Professor Van Doren.
Dear candidate, let me start by congratulating you the completion of your thesis. I'm also very proud to be here because you're the first PhD student graduating from the Dutch Black Hole Consortium, so very happy to see that and see that you were doing so well. Good. Of course, I enjoyed reading the thesis and I prepared some questions. I enjoyed actually the introduction that you wrote, where you briefly sketch also a little bit the history of that. And as a big fan of Oppenheimer, I was interested in what you wrote about Oppenheimer. And I was looking up some of the papers, but on page 139, all your references are nicely alphabetically ordered. I didn't see the references to Oppenheimer. Is that a little mistake or some conscious decision to leave him out of history? Or in the text you refer to Oppenheimer, but...
Yeah. Dear opponent, thank you for your kind words and thank you for this question. It's strange because in the PDF, I actually clicked on the reference and I found it. recently when I was checking through my paper, so I would perhaps need to look more carefully to find it, but it should be there. Sorry
of course,
about that.
it's a warm-up teasing question, of course. But I also recommend you to look at the Oppenheimer-Snyder paper, not only the Oppenheimer-Volkoff, but that's the one where they really predict gravitational collapse and black hole formation. Anyway, let's get to the serious business now in chapter 5. So it's very intriguing, these multiple images, of course, which you explained in your talk. And both theorists and observation, of course, interested in these multiple images. Well, first of all, is it really within near future that we can maybe see these kind of like secondary images, as you kind of seem to suggest? Is it?
Dear opponent, thank you for the second question. Well, we believe it is possible. Already, the Event Horizon Telescope is trying to make better algorithms, so in order to do dynamical imaging, to create movies, so have like really snapshot by snapshot. So if we have this sort of dynamical imaging and the hotspot is strong enough, it would be possible, even with the current arrays or a small improvement in them, and if we rely on an observation, to see. Now, it would be hard to identify if a brightening on the other side, it would be indeed, with the current observations, indeed from the hotspot, and it's a secondary image, or another brightening in the flow. But we can still analyze it and say, just in case this was this, we could infer the following for the space-time.
I see. Yeah. Okay. So on page 108, you start explaining numerical methods, and you say for the hotspot model, we use Boyer-Lindquist coordinates, and then for the ray tracing, we switch to Kerr-Schild coordinates. And then, as a theorist, I get very nervous because that's asking for problems if you're not careful, especially if you talk about the time lapse between the first and secondary image. Or so, is this now, this delta t, is that now expressed in Boyer-Lindquist time or in Kerr-Schild time, or what is the Yeah,
dear opponent, thank you for this question. So IPOL always works in Kerr-Schild inside the simulation because it's easier to handle, but the results at the end are always in Boyer-linguistic. So the delta t that we report at the end is in BL coordinates.
Okay, good. And so, okay, good. Then there is this kind of empirical approach that you have. And then there's this whole story. Now I just took the booklet out of the corridor, so let me look at the formulas where you kind of do some fitting or trial and error. Equation 5.11, you say like via trial and error we found the correct angle, and then I say, okay, what was this trial and error? What did you do? I mean,
dear opponent, thank you for this question. I computed this relationship in a Python script, and then I figured, okay, if I want to move, because this one is when we want to go to the first to zeroth to first order image, where typically this relationship is for n equals or reaching infinity, so really high order type of image. So I thought, okay, which part of this equation should I change to get to this? And I found this complete elliptical integral, k incomplete, that is written here in equation 5.11. Mm-hmm. So I thought if we're moving to an approximation of that, the first to zeroth to first order image, this integral shouldn't be complete but incomplete. So the way to do it incomplete is to remove the pi over 2 that it has in principle in the first bracket of the k incomplete. You see this pi over pi plus a star plus 0.3. This in principle, when it's complete, it needs to be 2. So I said, if to make it incomplete, I need to change this. I need to have a spin relationship because this makes sense. I saw it in the simulations. So I played with values and 0.3 worked.
I see, yeah. Okay, and then in 5.12, so you start from equation 5.4, and then you decide, let me erase a factor of 2 in the second term. I lose a bit confidence there, but maybe you can kind of put me at calm, at ease with this.
Yes. In this type of, this is even a bigger approximation, let's say. We just remove a factor of 2, and for most spins this work. this works just because the incomplete integral in the end of the day for small spins produces the same effect. Now, this is just even more, let's say, back on the envelope. Just have it in mind that if you read an analytical text and it says n reaches infinity, the order of the image, if you just remove 2, it's pretty close enough to what it should be for 0 to 1. So we just wanted to put this out there because it exists in the mind of some astronomers. Also, my co-author mentioned that. I would love to put this in written at some point. So yes, we thought it's a good opportunity talking about empirical relationships on this hard mathematical ground of secondary images to put it out there.
Mm-hmm. Well, it has to be, thank you. It has to be said, of course, that the theorists often cannot do better, or they make approximation that they do the difference between n and n plus 1 with n going to infinity. That's not very close to phenomenology, but could you give a grasp what simplified so much in the analysis there? Why did the theorists do this? How did they manage to get analytic results in that limit?
Dear opponent, thank you for this question. Well, the biggest simplification is that when you approach n equals infinity, then the photons always travel on the photon sphere. So they're on the photon sphere, and let's say that the twistiness when they come in and the twistiness when they comes out, this is perhaps also an intuitive way to think of this factor 2, is the same. They're being twisted from both sides when they come in and then when they come out. When we talk about the n equals 1 to 0 to 1, then in my mind at least, they receive only one twistiness, so it is the factor 2. And when you put it in the photon sphere, this is how you make the easy simplification of factor 2.
Okay, thank you. Yeah.
I'm afraid the time is up.
Time is up, so thank you very much.
Dear opponent.
Thank you very much. Next question will be by Dr. From.
So, dear candidate, congratulations to this nice thesis, and I have a few questions for you. The first one is, you talk about the galactic center. What makes the galactic center so special? And you went up to the near infrared, but is there more in the galactic center at higher frequencies and shorter wavelengths? And yeah, that's my first question.
Dear opponent, thank you very much for your nice question. Well, the galactic center is particularly interesting for us for a few reasons. One being, of course, proximity and abundance of observational data. But more in the theoretical side, it's very interesting because it's so dim that it doesn't even qualify as a low luminosity AGN, if you will. We don't know if it has, if it funnels a jet. It has a very small accretion rate. So it's really close to the ideal fluid limit, since the material there is so little dense. It's not dense at all. And the second part about high energy. Of course, there are high energy observations, in my knowledge for sure, in X-ray, and I'm not entirely sure about gamma rays, but we believe that X-ray flaring is a very important feature that really shows how even in this very dim disk, there are some dynamic effects, such as perhaps flux eruptions or the creation of hotspots, if you will, that do have signatures in high frequency, and hopefully in the future, if we explore that more in combination with the low frequencies that we study mainly, it would unravel more about these effects.
Thank you. But let's go back to the jet that you mentioned. Is there some indication that the galactic center had a jet in the past, or is there no way to judge this?
Dear opponent, thank you for this question. Well, I believe it's really hard to tell till this day. There are theories for both cases, really. Perhaps if we think at the most prominent theory right now for the accretion flow of Sagittarius A*, which is a magnetically arrested disk that has very strong magnetic fields, this is usually theorized. These disks are usually theorized that at some point in their lifetime they create a jet. So if we believe that this disk was from the formation or lasted a very long time, we can assume that it could have a jet going on at some point. But at the same time, the fact that we cannot see any remnants from this jet above the disk, above the galactic plane, is also a counterpart to that. It's really an active field right now.
Okay, thank you. So another question is that you developed all this machinery for the galactic center. Can you apply this to different sources? And what could you infer from those results? And can you make some conclusion comparing different sources with this method?
Dear opponent, thank you very much for this question too. Well, of course, all these pipelines are fully generalized in any source. I think what made Sagittarius A* such an appealing source as well is the time scales, where when you have a flaring event, it lasts for 60 minutes, let's say an hour and a half perhaps, while if you go to larger black holes, such as the M87 star, it's 1,000 times more, we would have to wait for months for such an observation. But actually, indeed, in larger scales as well, we see hotspots sometimes mentioned also in large-scale jets, as we heard recently also in a conference in Crete. So I am actually looking forward to develop or to explore also other sources with the same machinery and see what we can learn from that.
And my last question is, you start with the torus from the GMHD simulation. Are there different scenarios for the galactic center where you don't start there? And is there any evidence that there is such kind of a disk?
Dear opponent, thank you for this final question. Well, thinking about how the disk is being preserved in Sagittarius A*, which is mostly due to solar winds on the near vicinity of the stars in the near vicinity, it's quite possible that the flow is a bit more turbulent, or the way it's being formed, than a simple disk. And there are a couple of works trying to move towards to this direction. In the EHT, for instance, we do tilted disks, trying to emulate something similar, but it's not yet. It's not possible yet to feed a disk fully just from winds of a stellar population. So this is kind of the best possible scenario right now.
Thank you.
All right, thank you. The opposition will be continued by Dr. Atri.
First of all, a hearty congratulations on the thesis. I was particularly impressed with the depth of knowledge, both in the theoretical and the modern Bayesian inference techniques that you demonstrated throughout the thesis. That kind of brings me to my first question, which pertains to the Bayesian inference techniques. So throughout the thesis, it's been used a lot. But from the fourth chapter, I think, which was the Bayesian inference GRMHD on VLBI data, there you kind of changed your sampler to a more parallel tempering sampler, which is a great sampler, but I wanted to get your thoughts on why that was not used for the modeling earlier than this, and going back, would you use this sampler instead in the other modeling as well?
Dear opponent, thank you very much for your kind words and this first question. Well, indeed, partially it's due to software, partially due to the processes going in every different project. So in chapter 4, which is the third project of my thesis, indeed we use a more MCMC type of algorithm, both because it was found already inside Themis, which is the EHT framework that we use to do the complicated analysis of VLBI and compare it to GRMHT. But also later we changed to Dynasty that has what is this called? Dynasty, that is, I forgot his name. One moment, please. Yeah, nested sampling. Sorry about this small delay. Dynasty does nested sampling because we have more parameters, and we believe also that the distribution should be more bimodal. So we thought that for more parameters, a bigger parameter space, and also normal Gaussian distributions, Dynasty would be better. So actually we started on the Themis project, even though it delayed a bit, with classic MCMC. It worked well because we had only 4 parameters. And we didn't expect such bimodality in this project, and then we moved to Dynasty. So I think we would keep the current samplers for each project if we did it again too.
Wonderful, thank you. My second question is regarding chapter 2. So this is based on page 41. This is the best model that you ultimately think that should fit all parameters in this chapter. After the first step of spot fitting the ALMA data, then you try and compare it with the Stokes parameters and how that fits. In that page, you suggest that there is a mismatch in the Stokes I. That's because of some background issues. I was wondering why there is not such issues in the other Stokes parameters, the QUV.
Dear opponent, thank you very much for this very interesting question. Well, as a matter of fact, indeed, when we created the modeling of this hotspot, we differentiated the disk from the hotspot. So we did it in 2 steps. We first calculated the emission only from the hotspot alone, and then using 2 parameters, Stokes Q shadow and U shadow, that we attributed some component of linear polarization to the background. And then we went ahead and we recalculated the background alone using these 2 constraints, these new constraints for the linear polarization. This we did because the problem became too complicated and computationally expensive in particular that we had to break it down that way. So indeed, the hotspot we expected to give most of the effect on the QU parameters because the rest of the days is random. So it has to be the new thing that we add that gives this sort of character. And the background, in the end, we fitted it with a simple model with just 3 parameters. And indeed, the values we find, if you see, for instance, yes, if you see in page 40, we have the background models. And they're quite mismatched because they're trying to match at the same time the linear polarization background that we found from the hotspot, plus the other constraints. And usually they overshoot a bit in Stokes I, but there are a couple of models in particular, for instance, model 3 that they match well even Stokes I. But this is the main reason that we model differently the background and the hotspot when we did the analysis.
Okay, thank you. Do I have time for another question?
Yes.
Thank you. So now we've talked a lot about the bigger supermassive black holes. In the 5th chapter, you create a very interesting empirical relation, which we could get answers to black hole spins without necessarily measuring many other parameters. So I was wondering whether this empirical relation, in your opinion, could also explain the smaller stellar mass black holes in terms of getting their spin estimates out in a future era where we've got these amazing interferometers and we can do fraction of microarcsecond interferometry.
Dear opponent, thank you for this very nice question too. Well, of course, on the theoretical side, the physics around black holes are the same regardless their shape. This is particularly clear when we use natural units and we calculate everything in black hole mass, then everything is the same. So of course, it should be possible. Now, perhaps the most limiting factor again would be timing, because again, for a hotspot on a low supermassive black hole mass as Sagittarius A*, we need, let's say, 60 minutes. If you go to 10 solar masses, this is an order of magnitude of 5 difference. Because not only would we need to have very high angular resolution, but also very good timing. But if we were lucky enough, of course, it would work equally well in stellar mass black holes too.
Okay, thank you. That was my last question.
All right, thank you very much. And we now continue with Professor Jonker.
Dear candidates, also my congratulations on your thesis. It's a very nice and comprehensive work. I like the introduction very much, the historic timeline. And also what I appreciated very much is that you have different numerical tools and a large, diverse set of observational characteristics that you try to describe. This brings me to my first question, because in chapter 2, you describe your, for both Sagittarius A*, chapter 2 and 3. In chapter 2, you describe the millimeter light curve, and in chapter 3, the near-infrared astrometric and polarimetric data. But you fit similar parameters. You alluded to it already a little bit in your introductory talk. You don't get the same parameters. For instance, you model a hotspot, and in one case you get an orbital period of 90 minutes, and sub-Keplerian velocities, and in another case you get 70 minutes and so above Keplerian velocities. Do you have an explanation for that? Is it because you fit different observational factors? Is it a different hotspot? Are we looking at different hotspots? What is the feel that you have for that?
Dear opponent, thank you very much for this interesting question, also for your kind words. Indeed, this is one of the most interesting findings in this thesis, and we have a kind of a concept of an interpretation for all of this. The main idea right now is we believe that the hotspots that we observed with ALMA are on the equatorial plane of the disk, because this radio is where most of the emission comes in the radio frequencies, and perhaps in a magnetically arrested flow, where at some point the magnetic fields become so large and they push back the flow, they create this sort of hotspot in the plane that moves with the velocity of the rest of the fluid. So that should be the interpretation about the ALMA. Now, in gravity, there is also, first of all, we need to reach higher frequencies, so we need something, let's say, more energetic to reach these frequencies. And it is believed that either from the same effect, so when the flux eruption happens, the hotspot is being created in the middle, but also kind of like a lasso effect, as a rope, it also goes up to the jet sheath. And in the jet sheath, it doesn't have the pullback anymore from the flow that is moving subkeplerally, and perhaps there it can reach superkeplerian velocities as part of the same effect. So, for instance, if we had an instant observation, we would be able to see this, perhaps even with a small type difference, would be really the perfect scenario to disentangle this. Another theory about the superkeplerian motion and the high energy in general is that we could have the formation of plasmoids in the flow that are smaller blobs, again, kind of like hotspotty, but since they are smaller, we call them plasmoids, that happen in a smaller scale magnetic reconnection. Again, if they accumulate, we would expect them to move to the jet sheath, and that would explain, again, the gravity data. But for instance, in this case, we wouldn't have probably a simultaneous observation of the two. So this would be really the perfect way to disentangle.
Okay. So in the model that you now describe with hotspots that flow above the disk or start in the disk, flow above the disk, I guess unless it's really perpendicular, the inclination should change. But that's something that you can test as well. And so far, the inclination seems to be the same. So is that constraining this, or do you expect indeed this perpendicular flow from the disk in this description that you're...
Dear opponent, thank you very much. Indeed, the inclination plays a role, but when we talk for equatorial spots, it's pretty easy to describe. The problem comes, as we showed also in the last most exploratory model we created for the gravity data. When you put a hotspot above the disk, then in the projection, if the inclination is not face on, which it isn't, we know pretty well it's at 106, there is some degeneracy there of what is the projection of the hotspot that now is not sitting on the disk. So really, I was thinking about this problem, perhaps a more deep analysis, perhaps a neural network could help differentiate between an off-disk, an off-plane hotspot and the inclination. But with a good data fidelity, it should be possible.
Okay, thank you. That's nice for the future then, I guess. About the inclination, you now also mentioned that there should be a very good inclination. In those two chapters, 2 and 3, you have 155, whereas in chapter 5 you have 25 degrees for the inclination. Is this just a sign? Is it minus 25 and then it's 180?
Dear opponent, thank you for your question. Yes, we wrote 0 to 60 in the chapter 5 for simplicity, but it's fairly well understood or believed that the inclination of Sagittarius A* should be just on the other side, just meaning that the black hole spin axis should point away from us.
Okay, thank you. Is that still? So I have a very small question on the introduction. That is the last fallback. So here on page 14, you describe something that everyone needs. You have too many parameters and or too many degrees of freedom, of not enough data effectively. So you need something else in order to break this, and you use equipartition, which is quite common. You call it a theorem, which I think is quite strong. I would say it's an assumption. But could you describe why you think that equipartition is actually a good assumption in this scenario?
So you mentioned page 14?
Yes, in the introduction. It's just below the formula 1.35.
Yeah. Dear opponent, thank you for this question too. It takes me a moment to think back to this part. Right. I believe this refers to the fact that we should have the same amount of magnetic field scaling with the m dot, so that should happen all the way down to the horizon, and that's kind of, yes, as you say, perhaps an assumption that we commonly use to describe, to simplify accretion disk modeling and analysis.
Okay, thank you.
Thank you. And the opposition will be continued by Professor Koelink.
Thank you. Dear candidate, my congratulations on your thesis. It definitely has a very nice artistic impression of a black hole, so that's really very nice. Well, as you know, I'm a complete layman here in this committee, so I wanted to ask you a few questions about chapter 1, as far as I understand them. So I was a bit triggered actually by the history. So you start the history in your layman's talk, you start somewhere halfway the 20th century, but in your chapter 1 you start in 1784 with Mitchell and Laplace later on. And of course, well, as a mathematician, Laplace is a very well-known figure, but I was completely unaware of Mitchell. And then I noticed that I looked up the references and I tried to understand this a little bit. And you typically don't give a title of these papers if you refer to Mitchell and Laplace and some of the other historic references. Unfortunately, I could not download Laplace's paper, but it's apparently in German, which was a bit of a surprise. But you could download Mitchell's paper, and I was a bit, well, unaware of Mitchell, so I looked Mitchell up as well. And that's a very interesting figure, apparently. And actually, he also appears in this book by Bill Bryce, in A Short History of Nearly Everything. So that. But anyway, I looked up the title, and the title is a very long title, so let me just read a few words starting. It says, on the means of discovering the distance, magnitude, etc. of the fixed stars, in diminution of the velocity of their light, etc., etc. It goes on. So the title is at least an abstract. And this is actually a letter to Henry Cavendish, and it had to be read in the Royal Society of London. So I was a bit triggered and I browsed it a bit, and it's not easy reading, I can tell you, especially if you're not an astronomer, I guess. So my first question is, did you actually read this paper?
Dear opponent, thank you for this question. Well, these papers are kind of like well known as the first mentions in the astronomical, astrophysical community. So indeed, I didn't look past the title myself. It was always quite the read, as you just demonstrated. So no, I didn't read the paper fully.
But maybe you can still answer the next question following up. So I was wondering when I was browsing this paper a little bit. So of course this is an 18th century paper, and we are now a little bit further ahead. So there's a bit more knowledge about black holes, even a lot more knowledge. Could you maybe indicate to me what still stands from Mitchell analysis and what doesn't? Or
Dear opponent, thank you for this question. Well, if I do this, it will be mostly on the assumption of the mistakes Mitchell could make, and I would say it would be yes, to end up in the conclusion that there could be dark stars as that, he would have to guess correct the compactness of the black hole. So you need not only very big masses, but you also need the radius to be able to achieve that. So I think he would be able to reach that conclusion, and then miss out on all the super fascinating things that happen in the space-time around the black hole that were discovered later in the 20th century from Einstein and the theory of general relativity.
Okay, well, I think that's enough for the history. At least I learned from it, so that's, I think, at least for me, this is already a plus. I want to ask you a little, maybe a kind of not so nice question about your last part, because it's like picking your favorite child. But anyway, so if you look at if I look at your thesis from a distance, a couple of light years maybe, then essentially, in my point of view, these chapters 2 until 5, so these 4 chapters, kind of look kind of similar, right? So you have a lot of data, you have a model, and you try to fit it, right? So from that point of view, it's kind of 4 kind of similar chapters. So which chapter, in your opinion, is in a sense the best in this way of data fitting? And maybe you can also explain to me why you think this particular chapter is the best of your chapters.
Dear opponent, thank you very much for this interesting question. Well, I think the best results, the best chapter was probably chapter 2 with the ALMA fitting. That was for a few reasons all combining together. First of all, this dataset was the most detailed with a better fidelity data, so the smallest error budgets. For instance, if you compare it to the gravity data, the difference is like orders of magnitude on the errors. So this was really constraining for our models. And so at the same time, the radiation is computed in full consistency inside our code. So we use synchrotron radiation. We expect to reach exactly the correct levels. While, for instance, in the gravity paper, this is it's fractional polarization, so we don't have the same amount of information even in that regard. So I think our fitting was the most detailed. It had the better data to constrain the parameters. So it also made the most realistic predictions and also the most abundant ones. But it was also quite evident because it has been mentioned the most times the others. Now, personally, I also really love chapter 5 because it was more experimental and looking for solutions in maths and in coding. But yes, realistically, it should be chapter 2.
Okay, thank you.
Thank you. Thanks to the brevity of the questions and the answers, we're actually doing very well on time. So before I give the floor to Professor Falke to ask more questions, I ask the other members to think if at some point they have more questions. But I have a question, which I'm actually allowed to ask. In this general problem of using plasma or gas moving in around a black hole, I think there's a very fundamental issue that black holes are very simple, maybe not to calculate, but at least in principle, and so we know what to calculate. While gas and plasma and stuff it's not very simple, as we know when people are looking at stars and then maybe planets, and then you think about the weather. There's a lot of complexity, and so if you want to infer things about the black hole, like the spin, my question is, what is your opinion on, you can invest in very detailed modeling and statistical methods to extract things from your models, and of course you can invest in making your messy astrophysics models more realistic. Which of the two is limiting at the moment, and what sort of what steps are needed that at some point you can get a very good estimate of the spin in your models, because you're modeling whatever you put in your models already, and how does it relate to real spins in the real universe?
Dear Rector, thank you very much for this question. Indeed, it's a kind of a paradox, a very interesting situation, where black holes, as you say, they can be described with only 2 parameters, the mass and the spin. But when we add the so-called gastrophysics, so the plasma physics, the problem becomes quite entangled. Indeed, with roughly 2 million images of geometry simulations that are pretty much the best we can do right now in a global way, when we compare them to the image of the EHT, which is the most high-definition image we have, there is no way to disentangle the plasma from the space-time, the gravity part, the theory. So truly, you need to find an effect where you limit the most the plasma physics right now to do so. That's why Chapter 5 is so special in that regard, because it doesn't matter pretty much what sort of emission you have in this hotspot, as long as it's bright enough and the secondary image is bright enough to be seen. It doesn't matter in which frequency you are. It's a purely geometrical model anymore, because you just follow the null geodesics of the photons, and you have to do the imaging plane, but the plasma physics don't take any effect right now. So in the current moment, the most limiting effect probably is resolution, because the models can, if you have infinite resolution and you put all your zero image disks with all the different spins, you would be able, with a pipeline, to infer that. And so I guess due to the limiting of resolution right now, we need to look for more creative solutions or lucky observations to disentangle the very complex plasma physics from the space-time.
Thank you very much. I now give the floor to Professor Valke.
Thank you. Dear candidate, also from my side, congratulations for this beautiful thesis, including a theory as well. Thesis, including also the cover picture. I think, having given the black hole a dangerous red glowing color myself, and having called it gates of hell, it's nice to see a more joyful depiction and of black holes, which I hope is a feeling that you will have after the defense, and you radiate anyway, as a personality in our department. So I think that's quite fitting. I want to, before I come to my actual question, I'll come back to a question that was asked about jets. Of course, having tried to convince the community half of my life that there is a jet in the galactic center, you said we don't know. How would you then explain the flat radio spectrum in the galactic center that we see, which is the same that we see in all other AGN? And so do you need a different model for the flat radio spectrum, or would you explain it with a jet?
Dear opponent, thank you very much for your very kind words and also for this question. I'm not quite the observational person myself to know what the flat spectrum should mean exactly when I see it on a plot. But if I try to make sense of this really open question right now on the Sagittarius A-star system, and thinking of a recent talk I heard from Global Simulations of Lalakos et al., on global simulations on how the mud disks on very long timescales behave. Perhaps we are at a point in the lifetime of Sagittarius A-star where the jet either went off or it tries to push out, but it can't. So the whole simulation or the disk has characteristics that should produce a jet, but it has died out and it cannot push through the surrounding anymore to be visible. And so perhaps all the surrounding characteristics are similar to a jet situation, but it cannot really be produced.
Yeah, and I would also argue to keep in mind that this is one of the least powerful systems in the universe that we know, actually. Coming back to chapter 5, on one of the theses or the chapters that you like very much, there is between equations 5.6 and 5.7 on page 108, there's actually a sentence which is, actually appears twice, almost identical wording. Just in one case, it says, for the case of a moving hotspot on a circular orbit, you expect things to become very complex. And the other sentence, next time you leave it out. So is it really only for a circular orbit that you expect complex behavior? And secondly, what is it that you really simulate? Isn't your assumption that you are in a circular orbit, and isn't that a limiting assumption in your conclusion?
Dear opponent, thank you very much for this question. Indeed, I guess I was trying to mention that is a circular orbit as a limiting factor indeed, but I can see how it's stated a bit confusingly here. The circular orbit is a limit of our model, and if you had more complicated orbits, such as elliptical, it would be even harder to do this type. So I added just to mention that this is kind of a limiting factor, but it goes throughout the project, and it's not that afterwards something more complicated happens. This is a limitation of our simulation. That is a circular orbit and not a spiraling or elliptical one.
Which then brings me to the other question, because you actually have a parameter which allows for sub- and supercapillary motion. Wouldn't that then actually contradict the assumption of circular motion? And particularly, you also mentioned waves and spiral waves and so forth. And even though you don't mention it, that it could be in the jet, but could be as well. So, I mean, there are lots of reasons to assume that there is a non-circular motion, actually.
Dear opponent, thank you for the follow-up question. Well, you can have circular orbits also with non-Keplerian velocities as long as they are supported from the disk that surrounds them. For instance, inside the MUD simulation, all the fluid is moving at all times sub-Keplerianly because it's being dragged out from the magnetic fields. Now, indeed, you catch that the second simplification in this model is that we assume that the hotspot is on the equatorial plane. And again, if you would put it off equatorial, all this work would be super complicated. So I'm actually right now working again on a neural network, perhaps to have this library already feeded in with all the types of models and be able to differentiate from a full delta PA curve. But right now the circular motions with non-Keplerian velocities can, if yes, the system is near perfect, really nice, circular and equatorial can happen.
Yeah, it can happen, that's true. Section 5.3, you actually describe the model that you use. It was a 1 sigma radius of 1.5 m and a steep cutoff. What is the physical motivation for these parameters? You just assume them, or is there any reason why we should assume that is correct? Because if I think of reconnection regions, they could be very compact, very small. And if I have an extended plasma region, then the size of that plasma blob would actually matter and would shear as it goes around.
Dear opponent, thank you for this question. Well, actually, the hotspot size here, is motivated from other projects. In particular, the gravity project, where we included the spot size parameter as a free parameter, and we tested all the possibilities there, and we found that it converges around 1 or to 1.5 m. So here it doesn't really matter, again, unless, as you say, it becomes too large, so then it shears too much and you cannot track the centroid of the first image if it's too large. But in all other cases, it could be, the smaller it is, even the easier, let's say, but even with 1.5, so we put it as a general rule of a possibility, and when you follow the centroid, it's still sufficient to make this, to find the delta PA relationship between the first and second image.
Okay. Then I'll move on to figure 5.2, and there you show, and you mentioned this in your paper several times, that this method is independent of spin. Yet, you also mentioned this briefly in the text, we see that there's a bigger spread in this which you call the violin plot, but I think it's more trumpet plot, actually, if I look at the shapes. So can you give an intuitive explanation why it's independent of I and why the spread increases and where it comes from?
Dear opponent, thank you for this. This was actually both a very interesting and super important result, because indeed the inclination, even though it feels like a simple geometric parameter, is quite hard to model in GR. Now, the spread, of course, becomes larger and larger when you go to higher inclinations, because if you think, for instance, on an edge-on view, the hotspot moves almost always around the equator, so you can always see it on one side. When you go fully face-on, you have almost the same delta PA, because there is only one path the photons take behind the black hole to reach us. And so in all the in-between cases, you increase from one side to the other, from a very small spread in inclination 0 to the maximum spread where the photons come from everywhere when you're edge-on. Now, why exactly this happened is particularly strange, especially if you see in figure 5.1 that the full distribution of a delta PA in an orbit with inclination 60, let's say, as we see here, it doesn't even look symmetrical. It's not that it's easy. So it's a hard thing to tell intuitively to know why this happens. That the average delta PA on a full orbit is always equal to inclination 0, or very near. If you go pretty high, you see also it deviates a little bit. GR wonders.
Yes. Okay. Indeed. We try to get wonders explained sometimes, but it doesn't always work, yes. You give a prediction which is quite stunning, where you say that you get a spin measurement of plus minus 0.3 with 2 sigma coincidence based on your simulations. But then I wonder, isn't that a bit too optimistic, which you probably agree with? And I wonder how much you take into account the factor of UV coverage, which is limited. Also the fact of noise. I mean, how well you can really subtract the secondary image from the background, which also changes. And I can probably list a number of other effects which actually would make this much more difficult, is it?
Dear opponent, thank you for this question. Well, indeed, the 0.3 is, of course, with the current setup, and when hoping that the hotspot behaves, as I said, as nice and circular as we assume in the simulations. It is a good question to ask what happens if we inflate the errors. This is where I found them sort of realistic errors that increase a bit in percentage-wise. It's also, so I don't know exactly what happens if you increase the errors of the observation, but it's true that I should also check what happens if I just make the orbit a bit less ideal. That would also, so yeah, I'm not sure how that would increase, just changing the ideal situation that are described in this paper.
Maybe a last look into the future. You mentioned at the end some projects, NG, EHT, BEX. Glad you mentioned our own project as well here. You didn't mention the SHARP proposal, the EHI proposal that we had, which is sort of course beyond BEX. If you can choose, and we give you a lot of funding from the university because we know we're a rich university, we can really fund you a lot of science. And what would you do with it, in order to test your theory? You don't have to answer it, but you can.
Oh, that's strange freedom. Dear opponent, thank you for this final question, where of course I think space VLBI would be really the perfect experiment to test this type of observation. If we could have a resolution to see the photon ring, that would be already quite good on space-time results, but in particular in a hotspot observation, it would be the best case scenario to measure the most precisely the two images and their difference, and eventually the spin. So space VLBI would be probably, with a lot of money, the best case scenario.
Okay. We'll ask our university.
The defense is hereby concluded. I give the floor once again to the candidate.
Having defended my dissertation to the best of my ability, I would like to thank you, Rector, and you, my supervisor and co-supervisor, Monica and Maciek, and all who have honored this ceremony with their presence.
The Doctoral Examination Board retreats for its deliberation.
Where is it? Where is
just
the
fucked up alphabetically.
Oh my. But it's afterwards. You'll see, you'll see. I'll pick you up. Bro.
We got his next magic trick. Ah, but that's because it's a
Marlet.
No, but when they enter, we need to stand, right?
Yes. Let's go drink. Let's go drink.
On behalf of the Doctorate Board of Radboud University Nijmegen, we have decided to award you the degree of Doctor. I invite the supervisor, Dr. Mosibolska, to discharge the task assigned to her.
With the power entrusted by law to the Doctorate Board, I hereby confer upon you, Aristomenis Yfantis, born in Athens, the title of Doctor from Radboud University Nijmegen, to which are attached all the associated legal and customary rights and duties with respect to academia and society. As a proof of thereof, I present you with this doctoral diploma signed by the rector and the doctoral thesis supervisor and co-supervisor.
Please sit down. You can stay standing.
Okay, now I do. Okay. Dear Dr. Yfantis, dear Aris, esteemed Aris family and friends and everyone, we are gathered here today not only to recognize the academic achievement of a new Doctor of Philosophy, but also to celebrate a remarkable journey of Aris' growth and transformation as a researcher, as a thinker, as a collaborator, and also as a person. So let's begin with Aris' journey as a researcher. Aris decided to tackle one of the most challenging problems in our field, which is the variability of the most exotic objects of our universe. And to achieve his scientific goals, in 4 years, he learned literally from scratch everything he could on many possible black hole modeling techniques and numerical methods, on many possible observational data sets, their structures and their properties, on many possible parameter inference techniques using different experimental information. And this is just on the top of the entire complex theoretical background, including, all these simple topics, such as Einstein's theory of general relativity, or, for example, relativistic radiative transfer theory, and a few more. He also managed to connect all these different pieces of his research into a single story, which we know is today quite inspirational for many others. I couldn't have been more proud of Aris' learning curve and his research achievements. It was a pleasure to guide you during this journey. Aris comes also from the land of thinkers, Greece, so it feels almost mandatory to mention his achievements as a thinker. I would describe Aris as very perceptive, thoughtful, and creative. I didn't have to spend much time to explain to him, which projects could he do or develop. He somehow immediately knew what to do and naturally just started working. Yet he spent appropriate time on each of his projects, not rushing anything unnecessarily. What about Aris as a collaborator? It's important to know that Aris grew up as a scientist inside of the Event Horizon Telescope collaboration, where he helped to deliver to the public the second image of M87, taken only one year later after the first iconic one. Although this is not mentioned at all in his dissertation, I would like to highlight that he did find time to make his contributions to something greater than his thesis, already at this very early, very busy stage of a career. And I am deeply impressed by his commitment to do science for the sake of science, without taking any particular credit for it. So speaking of collaborations, Aris is also first PhD student coming out from our local organization, the Dutch Black Hole Consortium. And I would like to also take this opportunity to thank the consortium for their generosity when it comes to sponsoring Aris's travel related to work. We had a lot of them. And I suspect that the consortium support is also partially responsible for, what is Aris today. Yeah. And Aris was not only an exemplary PhD student, but is also extremely pleasant person to interact with. Your sense of humor, your memes became a highlight of our meeting and interactions, and your relaxed attitude to our profession and also exemplary, I would say, work-life balance taught me something. Ultimately, it's probably most important that we enjoy what we do. So I would like to congratulate you again on all your achievements, and also I would like to congratulate you on behalf of your co-supervisor. And we both wish you well and the best of luck in your future endeavors in Spain. And we both hope that you will keep up the good work and that you will find some happiness in your new home. Thank you.
It's my great pleasure to be the first after your supervisor to congratulate you on behalf of the doctoral board of Radboud University. Many congratulations for you, also for friends and family, both here and online. We have now come to the conclusion of this ceremony, and I ask you all to stand. We close with the following words. Gratias tibi agimus omnipotens Deus pro omnibus beneficiis tuis, qui vivis et regnas per omnia saecula saeculorum. Ladies and gentlemen. Wait. Should be a surprise. Wow. Can I have your attention?
You have to act surprise, wait.
I'm now here in a different capacity. I got rid of the chain, and so I'm here on behalf of the department because unfortunately Jörg couldn't be here and Marijke had to go home. So while I'm in the way of the important stuff, let's get this over quickly, but not too quickly. Thank you very much for being in our department. Monica already referred to it. You have a very positive influence on our department. Let's say it often enough, and please at some point correct me if it's not true anymore. We have a very nice department. We like to keep having a nice department, and it's great to have people like you in our department to contribute to it. We have a few presents for you to remember your time here, and we wish you all the best. And also we hope that sometimes you visit if you're coming back to your old friends here at Radboud. Thank you very much. Thank you very much. To the important part.
So, we have a tradition at the department that we give the person like a hat, an academic hat. We can just hold it like this.
Wow.
But because Aris is on the plane and he doesn't want to transport it, we took a more creative route by making a poster so he can just put it in a suitcase, so he doesn't have an excuse not to go through this. So we, his fellow PhD colleagues, design this usually arts and crafts hat, now a poster, with funny stories or character traits of Aris. And he now needs to do a second defense, which is go through all the things, in this case the poster, and guess what the thing is about and explain potentially the story behind it. So, Aris, the floor is yours.
This is amazing, guys. So start from the middle. I think I understand what this is. Yes, what? Not in the middle?
Usually you start chronologically.
Oh wait, introduction.
Because that's the only way no one
Wait
design
a
posters.
minute, this is harder. Okay,
Is this
sorry.
harder? Red couch?
Oh, this is a red couch. I understand now. Okay, this makes perfect sense. So, right behind of my desk in our lovely office, I have a red couch. Where when I started the PhD, first with Noemi, we used to take breaks there. It sometimes felt a bit like a therapy session. That's why it was the therapy couch, and the chair next to it.
What about the feta?
The feta is just me bringing lunch at the university. Usually with a lot of feta, also grabbing lunch there. And this sofa then hosted many dear colleagues. That was super nice. But of course, my first patient, my first PhD fellow, sister. Okay, can I move on?
Yes.
All right. So next we have what I think is me trying to publish my first paper that was rejected. That was kind of a shocker. It was already quite slow with collaborators and so on. So I guess it really was a motivation after that, I'll show you now what happened. So it was a bit of a slow, disappointing days. But then it, will you tell me if I miss
We'll correct you.
Okay. Then for great research, you need, of course, great funding. And what happened is that on the second year, we went for the Dutch astronomy conference in this fancy hotel. We were already circulating the idea of, we should bring some whiskeys, play some poker one night. I was already doing that a bit with my friends. So I said to the guys, okay, gather all around. We'll divide. Everybody was a bit reluctant to play with 5 euros buy but we convinced some people. The whiskey was flowing too much. So some people got a bit mad, some a bit
drunk and poor after the game, but it was super fun. You know, a real department bonding there. Wow. Now, methods. I need to start reading here.
Just go through
sorry, let's start from here. Okay. Aris's spare time activities. So, are you feeling active? No. Are you hungry? Yes, then eat at a food truck, just don't get food poisoning. That is because, of course, when in my travel to Mexico, I ate at the food truck. In the first day, I got a pretty bad food poisoning that lasted for a few more. So don't do that. I did it. I tried it for you. Okay, I'll continue on this line. So it was feeling active. No, hungry. No, feeling creative. If not, then explore the market. Buy nice, cheap pants. Exactly. Very importantly. Second, third-hand pants. Exactly. Feeling creative, then go to a drum jam session in the center of Nijmegen. That was quite a core Nijmegen weekdays indeed. Super nice. Then, if you're feeling active, back to the center, then do you choose minor violence? If no, then you're not choosing minor violence, you choose maximal violence, or not at all. Which is play beach volleyball, but mind the knees. That was the violence part, because of course I was playing a lot of volleyball, then I injured my knees, and I became semi-retired volleyball player, semi-retired walking, biking player really. But that was a lot of fun here in Nijmegen. Now, if you do choose minor violence, I guess is the important part, then play laser tag, where you may get stormed by kids. Well, this is another funny story. Because once in the Dutch Black Hole Consortium, actually, when all the PhDs were finally arrived, we said, okay, let's do an event and all of us meet together. And so the manager asked us for normal activities for PhDs to do. Go for coffee, something like that. Go for Amsterdam tour. And I replied first and said, let's go for laser tag. I think it's great. So some people started saying, yeah, sounds good. So then we arranged it. We arrived there, we were all playing. And halfway through, really, 15 kiddos, 8 years, come play with us and say, let's play teams. And we started being hunted from the other kid. Yes, when we met the Dutch Black Hole Consortium. So exactly, do that. You feel minor violence. Okay, results.
I would first go to conclusion.
All right, that makes sense. Well, this is amazing. Conclusion: the journey of Aristomenia. That's like kind of like the Odyssey. Aristomenia. Amazing. So let's see here. I'm assuming I must have started in Greece, so that should be here. But there are two ways that I will follow on the way that I know is the correct one. That is after Greece, of course, going to Tübingen for my master's, then coming to lovely Nijmegen. Thank you, Monica, for providing the opportunity to be here. That was super nice in the north part of the Roman Empire. And then after that, right now, making my way down to Spain, of course. Magic, thank you for helping me secure this next position. And so from there, I hopefully not go back to Greece. That's the tricky part. And I move a bit around and then...
Good to see family.
Yes, exactly. All right, so this is the conclusion of the trip and the results.
So, there's a final thing regarding the results.
Because your research was all about locating the hotspot on the black hole.
Yes.
But we made a small mistake and now you have to locate the hot pot.
Oh, exactly.
So the way this is going to work, you're going to wear a mask, spin you around, and then you're going to have to locate where the hot
really?
is. Do you want to?
Yes.
So it's like the tail and the donkey, but then the hot pot called the black hole.
Can you see anything? This says "Wake me up to eat," which I think is fitting.
Now see if it's equatorial or
That's good, okay.
You ready?
Yes.
There are like 3 times at most, otherwise...
But now I know where you are.
Oh.
Yeah, we don't want you to stick anyone in. So, him up a little bit, you go for it.
Okay, do you want me to try a bit to find the correct location or put it?
However you do your
I
science,
thought
right?
already it was on a different place. Listen, here is the black hole. Did you say so? Oh, wait a minute. Here's the black hole. The hot spots are on the sides of this, so I will go for here, you guys.
Yeah, just press it. Yeah, that's enough. That's that's
Good?
enough. Yeah. Yeah, you can.
Shall I leave it?
Yeah.
What the hell? It's amazing, truly. So I guess.
Tell us about your collaborators.
Oh yeah.
Yes, there are also a lot of pictures here. We have, of course, telescopes and conferences. We have. Why am I so happy here? One of the parties here in Nijmegen, of course, here with my friend Noemi, our PhD siblings. All of us in the horrendous place of Belgium, not old Belgium, the conference. Sorry,
he's fully integrated.
More drinks. It's usually drinks around here. Drinks, me saluting Einstein in Granada, legendary. This is me sitting at my classic office position. Exactly, yes, this both Wisma. Then barely you can see the bucket of mopping I used to put my feet through. It's quite visible when you enter the office. And more drinks, of course. So I have a moment also. Of course, I would like to thank really everybody for making this time in Nijmegen so amazing. It was super great coming every day to the department to such a lively and friendly atmosphere. I will miss it a lot here. It was super great. I hope all the best to you and indeed to keep to have the chance to visit very often, and in particular to visit my really beloved supervisor who truly made this such an amazing experience, both of course from picking me from the early days and then showing me all the super new exciting things that we could do together, and transferring me with all your immense knowledge and experience, and always of course leading me in the right way, in the right projects. Being able to finish on time, of course, is also due to your help, so thank you very much.
You're welcome. I can give you more projects.
Hopefully we will collaborate in the future. So really, again, thank you, everyone. It's been great. Let's have some drinks.
We still have some gifts for you. So So we of course also got you some gifts.
No.
Let's start with gift number 1. Don't drop it.
No, I got it. Can I take it out?
Yes.
What the hell?
Whoa, wait a minute.
Agus usually went for a pretty normal beer, but if I pushed him in the Irish pub, he would always want Jameson Black Barrel, right? So this is the more expensive edition.
So your whiskey.
Yeah, because otherwise you would never try it. But now he doesn't.
That's true. Thank you very much.
That's gift number 1. Let's do.
I'll wrap it for you. It's already pre-sealed. You might recognize we're inspired by you and your presence and also your scientific discovery. So this is a little t-shirt.
No way!
It's memes we made about you on a t-shirt.
Oh no!
He's the one they called memes this time around. So.
The plans are it, bro. This is so good.
Something about your pony immune system.
Yes, my pony immune system. Guys, how did you do all this? This is crazy. That's immune system. Proper statistics. Oh. Surprise! The quiz answer.
Yeah. So we actually wanted to give you before the defense, so that you wore it for the defense, but that was actually not allowed. So we now have to.
That sounds a little bit extreme.
So now for the drinks at 9 o'clock, you're going to
I
wear
will.
this t-shirt,
I will.
so that
I will.
everybody can come
Yes.
over and ask him about a particular meme if they really want to. And then a card.
Oh.
It's just a card.
It has all the wishes. Thank you. I'll read it later.
And
Most important gift.
Because you would cry.
Most important and secret.
What is the most important?
Bro, they're giving me money!
this is like a voucher and you can spend anywhere, right?
What the that?
Guys, really, thank you. You've been amazing paranims. A gigantic thank you. Come here.
You're welcome.
All right. Thank you all. So, planning. The drinks are at 9. You can go a bit earlier, I guess. We have, of course, the committee dinner at 7, so we'll meet you there. But feel free to go for some early drinks. I know I would.
These 4 key parameters for the hotspot, and you can see again in one simulation with high inclination how the hotspot is moving and the secondary image in response, and we're tracking the delta.
They all have been pillars of motivation. Παναγία μου. Chat που παίχτηκε εδώ.
Question.
My favorite paper.
Of course, I knew it.